I'd like to talk about extreme daily and subdaily precipitation in our climate models and how best to evaluate them, and more importantly, how best to interpret them. Extreme precipitation, even in a perfect model, must be lower than what is observed at the station. And in fact, we can construct a resolution constrained standard, which I show below, for 4 kilometers, 25 kilometers, and 100 kilometers. And you can see that as resolution increases, this standard that we would expect from the process of gridding alone is substantially lowered as resolution is coarsened. I've found recently that there's no improvement in extreme precipitation or temperature when going from the CMIP5 to CMIP6 models. Largely that's because there's little change in resolution. In fact, I find that CMIP5 and CMIP6 ensembles are interchangeable both in skill and in their projections of the future. Furthermore, in a recent paper in review, again, measured against this scale-dependent standard, there is even no improvement when going from CMIP6 at about 100 kilometers or coarser to high-res MIP, which is up to 25 kilometers or 20 kilometers rather in resolution. Indeed, extreme precipitation is higher in the higher resolution models, but no higher than would be expected from changing from one standard to the next, and the percent errors are the same. This figure here shows the changes from the low resolution models on the left panel or left column to the higher resolution models to the right of them. And you can see that for both of these models, the bias when compared against this resolution dependent standard is very little changed, with the possible exception of the CAM5. And so this indicates that the processes behind extreme precipitation, extreme storms in the winter in this figure, but also in the summer, are not improved by resolution. The improvement is only what we'd expect from this scale-dependent argument. So it asks us, we have to ask, are these models fit for purpose? And indeed, they might be for the pattern, although there again is no change between the high resolution and the low resolution shown in red and high resolution in blue in these Taylor plots showing pattern correlation and normalized standard deviation. So what do I think we need to do? Well, first of all, our extreme precipitation model performance must include this resolution dependence. Furthermore, we need to expand our diagnostics beyond bias maps, Taylor diagrams, and Gleckler diagrams to better understand extreme precipitation performance. Major questions are, why don't the high-res MIP models show improved process representations of winter and summer storms? In fact, we know they better represent tropical cyclone processes, albeit that's not in the seasons that I looked at here. Is parameterized convection to blame for poor performance in extreme precipitation? Generally, parameterizations of convection are not tuned to reproduce extremes, and they're certainly not tuned at these very high resolutions of the high-res MIP. It also begs the question, do we need resolutions higher than 25 kilometers to adequately represent strong gradients in temperature and moisture that are characteristic of extreme storms? Beyond the parameterized convection, are we representing the dynamics correctly? Finally, we need to develop some resolution-dependent scaling factors to utilize models. Because the models must have lower values of extreme precipitation than actuality because of this resolution constraint. How do we connect that to things like event attribution studies, where one wants to calculate a return period of a given amount of rain, or for driving a flood model, which may need to have the proper values of precipitation? And I think that statistical downscaling may be of some help here, but I'm not sure that it's particularly incorporated in current statistical techniques. Thank you.